Now that the front end is deployed, the next step is to connect it to our backend RAG system running in the cloud. That's where things start getting really interesting because we will move from a simple deployment to a fully cloud native AI system. Now, since we know that our RAG agent uses API keys which are very sensitive, so before we proceed ahead with the Lambda deployment, we first need to store the API keys as secrets in the secrets manager. So let's move on to the secrets manager first. Click on store a new secret. We will select the secret type as other type of secret, that is API key and token. We will give the name as AI knowledge base assistant open AI API key. Let's put an underscore. And here I'm going to paste the secret, that is the original API key. Now this is a very sensitive data. I'm going to pause the video for a moment, and once I am done putting the secret here and saving it, I'm going to resume the video again. I've stored the secrets. As you can see, the secret name that I have given at the end is AI knowledge base assistant secrets, and this contains my OpenAI API key. Now that we have configured the AWS Secrets Manager to securely store our API keys, the next step is setting up our vector database. In a RAG system, the vector database is where all the document embeddings are stored. Instead of searching through raw text, we convert document chunks into vector embeddings and store them in a vector index. Later, when a user asks a question, we convert the query into an embedding and perform a semantic similarity search against those stored vectors. So that's how the system retrieves relevant context. For this project, we will use Pinecone as the vector store. So Pinecone is a fully managed vector database. Its main job is to efficiently store and search embeddings. So whenever our system needs to find relevant information, Pinecone performs the nearest neighbor search on the vector space. This allows us to retrieve the most relevant document chunks in milliseconds. Here is the Pinecone console. You can see the indexes that are available. An index is essentially the container where all the embeddings are stored. Each index is configured with a few important properties. For example, the vector dimension, the cloud provider, the region, the capacity mode, and etc. In our case, we are using the on-demand capacity mode, which is convenient for development and small workloads. One important thing to note here is the vector dimension. Our index is configured with a dimension of 1536. This number must match the embedding model we are using. For example, the OpenAI embedding model text embedding 3 small generates vectors of size 1536. So the index configuration must match that dimension exactly. Otherwise, the vectors cannot be stored correctly. So I'll just quickly click create index. I'll give the name as AI knowledge assistant embeddings. I'll keep everything default, and here I'll just quickly cross check the configuration, the model configuration that we want to use. So this is the one that I'm going to use, text embedding 3 small, and I'm simply clicking create index. So our container for storing the vector embeddings for our knowledge assistant has been created. As a next step, I have also added the Pinecone API key to my secrets manager, as you can see in the screen. Now let me quickly create another S3 bucket to store my PDF documents. I'll give the name as AI knowledge assistant hyphen documents. Here I'll have this check on for blocking all public access because I do not want any public access to my bucket where my documents are kept. And I'll keep the remaining settings as it is. I'll click on create bucket. So my bucket has been created. I will now move on to Elastic Container Registry for storing the Docker images for our backend. So I need to first create a repository. I'll give the name as AI knowledge assistant, let's say repository. I'll keep the default settings as it is and I'll click create. So my private repository has been created. This is the place where we will be storing our Docker images. Once the Docker image is pushed to this repository, the Elastic Kubernetes service will fetch the image from this repository and run it inside a container. Now that some pieces of our infrastructure are ready, including S3, Lambda, and Pinecone, before moving on to the Elastic Kubernetes service, I would like to show you few changes across the code base to support the entire architecture. Let's walk through them. First, inside the API layer, we updated the dependencies.py file. Here we added a new dependency called get S3 service. The idea is to allow the backend to dynamically decide where documents should be stored. We support two modes, local storage and S3 storage. So internally, we added a small singleton function called get S3 service. This checks the environment variable document store backend. If the value is set to S3, the application initializes an S3 service. Then we expose get S3 service as a fast API dependency, which allows routes like the upload endpoint to easily access the S3 service. This keeps the storage layer flexible without tightly coupling the API to a specific backend. Now we updated the requirements.txt file. Since the backend now interacts with Amazon S3, we added the AWS SDK for Python, specifically Boto3. This library allows our application to upload documents to S3, download files, interact with S3 events, and handle object storage operations. Boto3 is essentially the standard AWS client library for Python. Next, we updated the env.example file. This file documents all the environment variables required to run the application. We added a new section for the document storage configuration. The key variable is document store backend. This controls whether the application uses local storage or S3. For example, document store backend equal to local is useful when running everything locally. But when we deploy to the cloud, we switch this to document store backend equal to S3. We also added a new AWS configuration section. AWS region, AWS bucket name, and AWS S3 prefix. One important note here is that AWS credentials are not stored in the .env file. Credentials such as AWS client ID and secret. Instead, authentication happens through IAM roles in production or AWS configure locally. This is a much more secure approach. Now let's look at the most important piece, the Lambda function responsible for document processing. This lives in a folder called Lambda. This function is triggered automatically whenever a file is uploaded to the S3 bucket. The entry point for the Lambda function is the handler method. It receives two parameters, event and context. The event object contains information about the S3 upload event. Inside the handler, we iterate through all the records in the event. Each record corresponds to a file upload. One small detail here is that S3 events %encode objects keys. So we first decode the key before using it. One important design decision here is that the Lambda function reuses the same services from our backend. So instead of duplicating the logic, the Lambda imports the document processor, embedding service, and the Pinecone vector store service. These are the exact same components used in the main RAG backend. This ensures that both the API service and the ingestion pipeline follow the same processing logic. The document processing pipeline. For each uploaded document, the Lambda executes the full pipeline. The steps look like parsing the S3 key, downloading the document, extracting the raw text, chunking the document, generating the embeddings, and then finally storing the vectors in Pinecone. Once this entire flow completes, the document becomes searchable by the RAG system. Now let's look at how the system handles document uploads using Amazon S3. Instead of sending the entire file through our backend API, we use a more scalable approach called presigned URLs. This logic is implemented inside the file app services s3 underscore service.py. The main responsibility of this service is to generate pre-signed S3 upload URLs and help manage document storage. Why we use pre-signed URLs? In many beginner systems, the front end uploads files directly to the backend server. But that creates several problems. The backend becomes responsible for receiving large files, buffering file uploads, handling network interruptions, forwarding the file to storage. This adds unnecessary load to the API service. Instead, we use pre-signed URLs. So here's how the flow works. The front end first calls our API endpoint post/upload. The backend then generates a temporary pre-signed S3 URL. The front end uses that URL to upload the file directly to S3. So the file never passes through our API server. Now let's look at the component responsible for storing and searching embeddings. The logic is implemented inside app services vector store pinecone.py file. This file implements a vector store service backed by the pinecone. In a rack system, the documents are first converted into vector embeddings. Those embeddings are then stored in a vector database. Later, when a user asks a question, we convert the query into an embedding and search for the closest vectors. The retrieved chunks are then passed to the LLMs as context. So the vector store is essentially the memory layer of the rack system. One interesting design choice here is that the Pinecone service implements the same interface as our local vector store. That means it supports methods like add chunks and search. Because the interface is consistent, we can swap implementations easily. For example, local development might use FAS, production uses Pinecone. This makes the system modular and extensible. When embeddings are stored in Pinecone, we also store metadata alongside the vectors, like I showed you during local testing. Each vector includes fields such as document ID, chunk ID, source file name, and the original text. This metadata is extremely useful during retrieval. So when the system finds relevant vectors, it can return the exact document chunk and reference information. So with all these changes in place, we now have a complete document ingestion pipeline. Users upload files through the front end. Those files are stored in S3. S3 triggers a Lambda function, and that Lambda processes the document and stores the embeddings in Pinecone. At that point, the document is fully integrated into the knowledge base and can be used during RAG retrieval. Now that the document processor code is ready, the next step is to deploy it to AWS as a Lambda function. Once deployed, the function will be triggered automatically whenever a document is uploaded to our S3 bucket. So instead of manually processing files, the entire ingestion pipeline becomes event driven. Let's set that up. First, we come to the AWS Lambda console. Then we create a new function. We choose author from scratch. For the runtime, we will select Python 3.14 and the function name will be something like rag document processor. We click create function. Once the function is created, we upload the Lambda code package that contains our document processor.py file. As mentioned earlier, this file includes the handler entry point that AWS Lambda will execute when the function is triggered. Next, we configure the environment variables required by the function, such as Pinecone index name, embedding model configuration, etc. So we scroll below, we see the environment variables here. Click add environment variables. And let's add our environment variable here. So I've added all the necessary environment variables. In production, some of the values such as the Pinecone API key and the OpenAI API key can come from AWS Secrets Manager as mentioned earlier. This allows the Lambda function to securely connect to the vector store. Now in the lambda slash document processor.py file, I mean the file which we just uploaded as a lambda function, we had added a function called load secrets to env. This function fetches the secret once at cold start, that is the module import time, and the secrets loaded flag ensures warm invocations at zero cost. Reads secrets manager secret name from lambda environment varies. So it parses the JSON string and injects each key into the os.environ. Now we need to attach an IAM policy to the lambda execution role to allow the function running inside lambda access the secrets. But before that, let us deploy this function. So to add the IAM policy, go to the configuration tab, and here you can see we already have a role for the execution role called the RAG document processor role, this one. So you click this, it will open the IAM console in a new tab. So you just click on this policy, select the JSON tab, and here click edit. Now you add another object, allow, action. It will be secrets manager colon get secrets value. Another alternate way is to select the AWS service from the right hand side pane. Then comma, then we need to indicate the resource. So resource, and we need to give the ARN number of our secrets. So I'll go to my secrets manager again. So I'll just copy the ARN of the secret, go back to my policy and paste it here. Once done, click on next and save changes. Now comes the important part. We configure the S3 event trigger. So inside the Lambda console, we add a trigger and select S3. Let's go to triggers, click add trigger, select the source S3. Then we need to choose the bucket where documents are uploaded. In our case, it will be AI Knowledge Assistant documents. Now we select the event type as object created. So this is the one, all object create events. This means that every time a new file is uploaded, the Lambda function will automatically execute. So the flow becomes user upload to S3 to Lambda, then document processing, and then to the pinecone. Click add. So let's quickly recap what happens now. A user uploads a document through the front end. The file is stored in the S3 bucket. That upload triggers the Lambda document processor. The Lambda function then downloads the file, extracts the text, chunks it, generates embeddings, and stores those embeddings in Pinecone. So to test this, I'll upload a document directly into the S3 bucket. Once the file is uploaded, S3 should immediately trigger our Lambda function. So let me go inside my bucket, AI Knowledge Assistant documents, and let me try uploading my PDF files. So I'm going to AI Knowledge Assistant, Agent, and these are my document. Let me try uploading this three. Let me click upload. Yeah. So you can see the files appear here in the bucket, and in the background, Lambda will begin processing the document. So now let's open the Lambda logs in CloudWatch. So let me go to CloudWatch. Let me go to logs, log management, and this is my log group, rack document processor. Let me select this, and you can see there are two logs that has appeared here. Let me click this. So you can see I have received few logs in here, and it says, so it initially tried to upload, sorry, process the PDF here. If I go to my Pinecone database, and if I go inside my index, AI Knowledge Assistant embeddings, and here you can see the embeddings have been inserted. So if I click here and if I click fetch, so you'll be able to see the text in here, the original text of the PDF, and these are the values. These are basically the processed or the converted values, vector values. This is what we were talking about, the vectors. So yeah, so likewise, if I keep uploading the other two documents, it will do the same here. So it will create two more records for the other two documents, and our job will be done. So here we can confirm that our Lambda processing pipeline, or in other words, the document ingestion pipeline is working perfectly.